Hello, my name is Nicholas Verostegui, and my project I am presenting today is development of the Rust language compiler for AFTx06 chip and development of sample applications. This project aims to create a Rust-based front end for the LLVM version used by Purdue's System-on-Chip team. This will run Rust-based LLVM code through several sparsely supported passes, and then go through the backend and produce machine code. The goal of this project is that this machine code will then be compatible on the AFTx06. Now, the AFTx06 is an application-specific integrated circuit, or ASIC. This integrated circuit design supports sparsity. However, testing will be done on a field programmable gate array, or FPGA. The FPGA is a chip with reprogrammable logic, which is ideal for testing if we decide to change the design, as we can reprogram the chip without having to order a new one. The AFTx06 chip will be running off a RISC-V core. Now, what RISC-V is a type of instruction set architecture, or ISA. ISAs specify machine code behavior. It would be accurate to think of it as the interconnect between software and hardware, and is unique in its stability and simplicity. RISC-V is much more clean and cut compared to other architectures, making it faster and easier to manage. Our particular RISC-V implementation supports sparsity. Now, I mentioned LLVM, and what that stands for is the Low-Level Virtual Machine. It's a project that consists of compiler and toolchain technology. The diagram here is how a typical LLVM version works, with C or C++ code being ran through the Clang compiler or the LLVM front end into intermediate representation or LLVM IR code. This IR code is then ran through several passes through what's known as LLVM proper. These passes are what make LLVM unique, as they're very modular and can be edited by the programmer as they see fit. So new passes can be introduced or the existing ones can be edited. The IR code is then ran through the backend, which outputs machine code. Now, our particular LLVM version uses sparsity in the passes, which I'll explain now. Sparsity is the ability to coder dynamically choose which instructions to execute. And it does this by generating a sparsity-aware skip address table, or a SASA table. So it identifies redundant code, and the table will then indicate which instructions can be skipped. The most prominent example is that within sparse matrices. Because sparse matrices include mostly zeros, there's a lot of redundant instructions when executing them. So sparsity would be able to find the redundant instructions, in this case the majority of the zeros in a sparse matrix, and choose not to execute them. Now, the reason why we want to create a Rust front end is because Rust is a multi-paradigm language and a strong competitor with C and C++. It provides strong static guarantees, and it's significantly harder to make mistakes in Rust that are very common in C. For example, in C, it is a common mistake that the programmer may access memory that either they do not have access to or simply does not exist. Rust solves this issue. It's significantly harder to make mistakes of that type. So it gives precise control over data layout and memory management, but still has the high speed and stability comparable to C. So developing a Rust front end would be a great way to benchmark progress on the chip, and will open up opportunities for more applications on the chip, with machine learning being a prominent example. And in addition, we hope to port a Rust-based operating system on the chip, which would help to create a more secure computer. So how we develop this code, or how we integrate it into LLVM system, is that we start with Rust code and compile it through a Rust-C compiler to produce LLVM-IR. This LLVM-IR is then run through the Clang compiler with flags to indicate to run it through specific sparsity-based optimizations, or the passes. This will produce a SASA table and assembly code. The assembly code is then compiled through GCC into machine code. And as a result, we were able to successfully admit LLVM-IR. The admitted IR was compiled into the desired binaries, and a SASA table was produced. the type state module was successfully implemented. However, the current LLVM version can only compile bare metal Rust. And what bare metal Rust is it's Rust code that there is no pre-compiled Rust code, meaning that the standard library or external crates that most programmers would typically have access to are non-existent. So any implementations with particular data types or any particular functions would need to be implemented in the code itself versus imported. But running Rust code on producing binaries based off Rust code is proof that a Rust-based operating system could run on the AFTx06 chip, with the main issue being the limitation posed solely by bare metal Rust. Further work will have to be done to include external libraries in future research. Here are my references, acknowledgements to my mentors, and as well as funding from the Scale program. This concludes my presentation.